design of concrete structures, reinforced concrete design, short columns, example number 1. In this example, we do have a short concentrically loaded round tight column shown in figure which is handling a dead load of 150 kilopounds and a live load of 350. Mhm. If we know all the longitudinal bars has the same cross-sectional area. Mhm. We want to know what is the minimum required size, what is the minimum required size for each of those longitudinal reinforced bar. We want to have a report of bar size by their number, bar size of something like 9, 10, 14. Mhm. So these are the longitudinal reinforcement. At the same time, a yield stress of a steel for rebars are provided to be 60,000 pound per inch squared, and a specific strength of concrete F prime C is provided to be 4,000 pound per inches squared. To solve the problem, first of all, there is a resistance reduction factor in mm, members with ties. So that's a phi, which is 0.65 times a nominal axial force in column, mhm, which should be greater than ultimate load, which is a combination of live and dead loads. Mhm. So PU ultimate load, ultimate axial load of short column is equal to a coefficient times dead load plus a coefficient times the live load. And the reason that the coefficient of live load is higher than the dead load is a we have a rough estimate of live load in comparison to dead load, because dead load is mainly the weight of the structure itself, and it's predictable, and live load is a a combination of the numbers of a people, or they're concentrated of the live load. So that's a more unpredictable in comparison to dead load. Mhm. And we have a nominal axial load of a column, which is again another reduction coefficient, and that's 80% of P naught. Mhm. And we define P naught for columns that which is 85% times F prime C, times area of concrete plus A steel area of rebars, which we are looking for right now, times the yield strength of steel, which is provided here. Mhm. So first of all, we calculate ultimate axial load, and that's by replacing the dead load and live load by their coefficient, we get a PU is equal to 740 kilopounds. As soon as we have PU, we can now first we need to determine the amount of reinforcing steel required by minimum required reinforcing ratio of rho g. So ACI code just gives us a limit for a limitation for main reinforcement, which is a longitudinal reinforcement. Mhm. And that's a rho g should be higher than 1.0 and should be smaller than 0.8. Mhm. and that consider rho g is A steel over A gross. Density of rho g is equal to area of steel over the entire cross-sectional area. So that's 0.01. Knowing that A steel is a rho g which is provided by the code, and that multiplied by a quarter of pi times d squared, which is the area, diameter, and area of the entire section, which is gross section. And if you do the math, it just gives you almost 2.5 inches squared. Now we need to determining the amount of reinforcing steel, this time based off of factored axial load Pu. So we had one minimum area for a steel or longitudinal bars. We need to calculate that's for the minimum of the ACI code, and the other one is from the calculation, then compare, make a comparison between them and choose one. So Pn nominal axial load is 80% of P naught, and P naught is 85% times a specific strength of concrete times area of concrete plus area of rebars times Fy, which is the only unknown if you replace that, and then phi, which is 0.65 reduction resistant reduction factor times Pn nominal axial force should be higher than Pu, which we already calculate this one. So if we replace that in the formula, 0.65 times 0.8, which is come from here, times a P naught, because Pn is equal to 80% of P naught, so these two is just the coefficient, times then start from P naught here, 85% F prime C AC. It just comes from the main formula, 80.85% F prime C times AC. We have the same, plus A steel area of longitudinal rebars times Fy yield stress of steel. And that should be at least equal, or if not bigger, at least equal to a Pu ultimate, which we calculate to be 740 kilopounds. We just convert that to pounds. This coefficient goes by 0.52. And if you do the math, it just gives you, if you divide the second part by this coefficient, it just gives you 1423 point something 10 to 10 cubed for the second part, and it just gives us an equation just based off area of steel, and it just gives us area for longitudinal steel is equal to 9.86 inches squared. And area for longitudinal steel, the minimum of the ACI code is most of the time the minimum level for the design, but area of steel longitudinal is the maximum of minimum for ACI code. That's the minimum of ACI code, and AS calculated from the Pu and the axial force equation of short columns. And if you do the math, it just, if you remember, the minimum calculated was 2.54 inches squared, and the calculated is 9.86 inches squared. and the maximum of them is definitely AS calculated. And if you again look at the figure, you can easily see 1, 2, 3, 4, 5, 6. We do have a 6 longitudinal rebars. So A for each of them is total area, which is 9.86 over number of the bars, which is 6, and it just gives us 1.64 inch squared over bar. Mhm. And if you look at the table for the bar size, this is between number 11 and number 14 bars, which are the available bar size in the market. So this is a more close to 11, but in terms of design, we are interested in decreasing the stress, so we choose to go with the higher uh, area. So that's a bar size number 14, and we choose the higher area. By increasing the area, we decreasing the stress on the bar and structure, and that's in the direction of increasing factor of safety. We'll work around to solve more example in short and long columns, slender columns, and in next few videos. Thank you.